Welcome once again to Further Solutions Academy. Please share and subscribe to our YouTube channel, and you can also reach us or via this contact +2348034495990. Either you can call us or reach us on WhatsApp or on the Telegram social media. Please do well to share and subscribe. If you can either you can comment on the YouTube channel, or you can give us a personal message on those social media, or you can give us make a contribution, or even ask further questions that you are not or you need clarity on. So for today, we'll be making a continuation of gas laws and calculations that we started in our last class. And like I said earlier, like I said in the last class, today we'll be going through about more laws which we have started earlier. So today we have done Boyle's law, we have done Charles' law, and the general gas law. So today we'll be going into the ideal gas law, the ideal gas equation rather, the ideal gas equation. A better understanding of the ideal gas equation is from the notation that we had in our general gas law, which says that our PV is equals to KT. Which says that our PV is equals to KT. Now, where did we get this? This was gotten from a combination of our Boyle's law and our Charles' law. So we had our PV to be equals to KT, where we have K as our proportionality constant. Now, any gas that conforms to this particular equation, the way it is, not at different temperature and pressure, but probably the temperature and the pressure at a particular is kept constant, is known as an ideal gas. Is known as an ideal gas. And for this reason, for the gas to conform to this, it means our K is constant. It means that our K is constant, or it could actually be our gas constant. It could actually be our gas constant, but for better representation, if you check textbooks very well, you realize that PV is equals to RT, where our R is our gas constant. It's just a substitute for K, actually. So you would see R in basically more textbooks and online and different places, different sources or references. You see R as our gas constant. Now, this ideal gas, that means a gas can conform to this equation when it is it has a constant value. It has a constant value, and at 1 mole of the gas. At 1 mole of the gas. So this equation works for 1 mole of the gas. But if we want to ask or check for other moles of the gas, we can rewrite this to be PV to be equals to nRT, where our N is equals to N moles of the gas. So it could be 2 moles, it could be half mole, it could be any mole. But there is something we need to know. So this equation is actually the ideal gas equation. But one thing you need to know is this particular value, your gas constant, which is your K or your R, but basically or usually your R. R has different values. Please take note. And the values of R that we use is related to the unit of the other parameters you are given. Basically, most usually, you use R to be 0.0821 sometimes. Now, this is when you are using your pressure in ATM, your volume in liter or dm cube, then per mole, and your temperature per Kelvin. Now, you can also use your R or see your R to be 8.314. Now, in this situation, your R is usually in joules per Kelvin per mole. And for it to be joules, it means probably you are using Pascal, and instead of liter, you are using meter cube. Yes, Pascal and meter cube for for the pressure and the volume for you to get. So what I'm saying in other words is always look at your unit of the other parameters and determine the right value or the appropriate value of R to use. The appropriate value of R to use. Now, usually you would have seen questions, we would have solved a question that is direct. Okay, let's say let's just play with a question that says calculate the number of moles of a gas with its volume of 300 centimeter cube and a pressure of let me use 3 liter on this, and the pressure of 1 atm with a temperature of 20 degrees Celsius. So sometimes your R could be given and other times it is not given. But judging from the concept of what I have my volume in liter, I have my pressure in atm, and I have my temperature in Celsius, but this can be converted to Kelvin. So my R is given as 0.0821 atm liter per mole per Kelvin, right? Per mole per Kelvin. Okay, so I have to convert this first, which is 20 plus 273, which is 293 Kelvin. So how do we do that? PV is equals to nRT. So my N, which is my number of moles, is equals to PV over RT, where my pressure is 1 times 3 over R, 0.0821 times my temperature, which is 293 Kelvin. This can be calculated, and the answer is 0.125 moles. Remember, we are looking for N. So this is a way you can actually find a question, but you can also find some questions based on your interpretation or how you can further your formula. Let's assume we have a question where you are told to calculate for the mass of a CO2. Calculate the mass of CO2 with a volume of, that's 11.2 dm cube at 27 degrees Celsius and a pressure of 10 kilopascal. Okay, all right. So now you are told to calculate mass, but our formula is PV is equals to nRT. Now, from your basic chemistry, you realize that your N is equals to your mass over molar mass. So you can also further this formula to be PV is equals to mass all over molar mass RT. So my mass will be equals to PV times my molar mass all over my RT. But the R that is given in this question is R is equals to 8.314 joule per Kelvin. Our R should be 8.314 joule per Kelvin per mole. So this, substituting this, my P, which is my pressure, I need to So this is the formula to find the mass. But I need to change the units to meet this. Because I told you earlier that this R, when it is given, it is not in dm cube any longer, but in meter cube. So if I want to do that, I need to convert this to meter cube. And 11.2 dm cube is equals to 0.0, that's times 10 raised to power minus 3. That's times 10 raised to power minus 3. That would be 112 meter cube. 1, 2, 3. Yes, meter cube. Then my pressure 10 kilopascal is equals to 10,000 pascal. Then my temperature 27 degrees Celsius is equals to 273 plus 27. That should be 300 Kelvin. I think we are good to go. So our molar mass of CO2 is, carbon is 12 plus 16 times 2. That's 44 gram per mole, right? 44 gram per mole. This is 12 plus 32. That's 44 gram per mole. So if I'm following this, my M is equals to my pressure, which is 10,000 pascal, times my volume 0.0112 times my molar mass of 44 over my R, which has been given 8.314, times my temperature of 300. If we should solve this, you realize that we'll be having an answer of 1.98 grams as our mass. 1.98 grams as our mass. So our mass for this question is 1.98 grams. Why are we doing this? It's because to see that there are dynamics there are different ways by which your question can come forth. You will not necessarily be asked for the number of moles. Sometimes you may be told to find the mass, and other times you may even be told to find the molar mass of the given gas. So either ways, just ensure that you keep this formula at the back of your mind, and so that you can remember it often. So that is that on the ideal gas equation. And the next law we'll be going to is the Graham's law of diffusion. The next law we'll be going through is the Graham's law of diffusion. Graham's law of diffusion. So the next law we'll be going to is the Graham's law of diffusion. You must realize that before we go into Graham's law of diffusion, that gases spread and they are always accessible to the volume occupied by them. That means if you put a gas in a volume of about 20 cm cube, they are able to spread across. Remember that under the kinetic theory, the molecules of a gas are actually free. They're actually free. The forces that holds them are actually weak forces. So they can actually move and conform to the whole volume of that container that is 20 centimeter cube. So under this condition, how do they move to fill the whole volume that they are accessible to? It's through a process of diffusion. And diffusion, from what we know, is actually a process that which gases move. So what is Graham's law of diffusion saying? This law states that the rate of diffusion of a gas is inversely proportional to the square root of its vapor density. To the square root of its vapor density. Some will say density, some will say molecular mass. I will explain to us as time goes on which of the following you can actually use and how you can use it. So what Graham is saying mathematically, let's quickly have, I believe we have this already. So what Graham is saying is that the rate of a gas is inversely proportional to the square root of the vapor density. Some will put Vd. You can as well represent it as D. So supposing that the rate of diffusion of two gases under the same condition is examined. So that means the first one will be R1 is equals to 1 all over square root of D1. Then the second one, R2, will be equals to 1 all over the square root of D2. 1 over the square root of D2. So if I want to combine these equations together with my R1, that means my D2 will be 1 over R2. So if I combine them together, I have my R1 over my R2 to be equals to the square root of my D2 over the square root of my D1. That is gas 2, gas 1, rate 2, rate 1. So I have this. But do you recollect? Remember now, this is one formula. Now, recollect that our vapor density is equals to our relative molecular mass over 2, right? So that means I can substitute this vapor density for my relative molecular mass. Let's just play around with that, where I have R1 over R2 is equals to the M2 over 2 all over M1 over 2. This can further, bringing this out, I have M2 over 2 times 2 over square root of M1. This. So I'm left with M2 over M1 still equals to this. So my rate 1 and rate 2 is equals to still the molecular mass of my rates. Okay, 2 over M1. This is another formula under Graham's law of diffusion. So substituting this, I can still have this formula based on the parameters given. Sometimes you may not be given the vapor density, you'll be provided with the molecular mass, and you are still expected to get the rate of each gases. Now, another thing we can actually subject this to is with respect to what our rate is. Our rate is equals to the volume. To find the rate of a gas is the volume covered by the gas over the total time taken. Total time taken. So R is equals to V over T. Now, if R is equals to V over T, we can still get other formulas relating this together. So if we okay, let's continue from there. Let's continue from there. So if we subject that formula, which is R is equals to V over T, please, in small letter. Capital letter is for temperature, T is small letter, in seconds or whichever time that we are provided with. So suppose we are given two different gases that actually have equal volumes. So imagine we have two different gases. My R1 will be V1 over T1. Then my R2 will be equals to V2 over T2. Now, supposing these two gases have the same volume. So that means I can combine this equation to say my R1 over R2 to be equals to my T2 over T1. How? By subjecting it inversely to get the time, because volume is actually the same. Or it could have been said that the volume is constant, which I could represent this as 1 1, and to get my this, that means the inverse of this, and this representation will definitely provide us with something like this. So if my R1 over R2 is T2 over T1, recollect that my R1 over R2 is also equals to my D2, square root of D2 over D1 is also equals to molar mass 2 over molar mass 1. Now, this R1 over R2 is also equals to T2 over T1. So this is the third formula that we can actually get using Graham's law. So I can say that my T2 over T1 is equals to the square root of the molar mass of 2 or the square root of the molar mass of 1. This is another formula that we can get under the Graham's law of diffusion. Let's just play with the question and see how far we can go with that. Let's try solve a question before we end for today and see how far we can go with that. Okay, it says a certain a certain volume of hydrogen gas diffuse through a porous partition in 25 seconds. That's for the hydrogen gas, and you're told to calculate the time required for the same volume. Now remember, we talked about the same volume of hydrogen chloride gas to diffuse under same conditions. That means we have two gases. We have the gas 1 to be hydrogen gas, and we have the gas 2 to be hydrogen chloride gas. Now both of them have the same volume. Remember, we talked about the same volume and the rate proportionality to the time. Then now we are also left with they are under the same condition. When we are provided with hydrogen molar mass, atomic mass to be this, and chlorine atomic mass to be 35.5. Yes. The reason why we need to get this right is because under the molecular mass of Graham's law of diffusion, please realize that your molecular mass is the relative. So that means if you are using let's just solve something like let's solve that. So my time taken for hydrogen gas is 25 seconds. Right? My time taken for HCl is not given. But I can realize that since I've been given the atomic mass, the best formula for me to use is my time with the molar mass, which is T of this is equals to my molar mass, relative molecular mass of hydrogen over relative molecular mass of HCl. Yes, I want to believe we are right on that. Okay, so my relative molecular mass of hydrogen, it is relative, but please, I have two hydrogen atoms in an hydrogen gas. I have two hydrogen atoms in my hydrogen gas. So this, my relative molecular mass of hydrogen is not just 1. It is 1 times 2, which is 2. Then the one for my HCl is 35.5 plus 1, which is hydrogen, and chlorine is equal to 36.5. The reason why you need to do this is some make the mistake of just using 1, assuming it's an hydrogen atom. No, you have 2 molecules of hydrogen gas there. That means this is 1 times 2 because it's the relative. So imagine if you were to solve for the ozone. You have to find the relative molecular mass of ozone. Please, you know this is what? 16 times 3. The relative molecular mass for ozone is different from that of oxygen gas, because there are some questions where you'll be given oxygen gas and ozone under similar conditions, and the relative molecular masses are not going to be the same. Please watch that also and be very careful of that. So if we can do that perfectly, I believe we have our equation and we can get our answer. So we say that our time for this is 25 seconds, right? All over T HCl to be our square root of 2 over the square root of 36.5. If I believe we can solve this mathematically by squaring both sides. Square both sides. So if we square both sides, it becomes it becomes 25 squared over T squared of HCl to be 2 over 36.5, because it eliminates the square root sign here. So this becomes 625 over T squared of HCl to be 2 over 36.5. Right. So if we should cross multiply, we have T squared of HCl. Remember, our T here is squared, is equals to 625 times 36.5 divided by 2. I want to remove this square, so that becomes T of HCl to be square root. That means square rooting both sides back to remove this square. Because all I'm looking for is time, not time squared. That becomes 625 times 36.5 divided by 2. So the time taken from a hydrogen chloride gas to diffuse will be 106.8 seconds. 106.8 seconds. You can confirm that with your calculator, and that is the time taken for hydrogen gas. Now, other times you may relate it with density, you may relate it with molecular mass, you may relate it with your rate. Just be careful, watch the parameters you are given and how you can go about it. And that is all for today. We've talked about the ideal gas equation and Graham's law of diffusion. So see you next class where we'll be discussing on Gay-Lussac's law of the pressure law and Gay-Lussac's law of combining volumes, as well as the Dalton law of partial pressure and Avogadro's law. See you next class. Don't forget to share and subscribe. This is Further Solutions Academy. Please do well to share and subscribe our YouTube channel, and reach us via the contact that was shared earlier for any details or any contribution, comment, or further questions on clarity you need on any of our videos. Thank you. See you next time.